A problem of great interest these days is pattern recognition in data. For instance, how can I get software to recognize handwritten characters? One way you might do this is to take a bunch of handwriting samples of known characters. For instance, suppose we have 500 people who have given us writing samples of every character of the alphabet, and a computer has scanned these samples into pixelated 8x8 grids. For a given sample, that's 64 bits of information that represents how much ink was in a certain position on the grid. For instance, we might have several letter J's recorded like what you see here. These all vary a little bit from each other since no two people will write a J exactly the same. Now suppose someone submits a letter sample like this one. How can you write software to determine what character this is? Is it a J? Or is it an M, or C, or an A? Here's where mathematical visualization can help us, even if abstractly. Each of the 8x8 grids can be written as an ordered collection of 64 numbers just by reading each row in succession. As we shall see, this could represent a point in 64-dimensional space. Viewed this way, I have a bunch of writing samples that represent points in space. There's a cloud of points representing the letter J, and another cloud of points representing the letter M, and another cloud of points representing the letter C, and clouds of points representing the other letters. Some of these clouds may overlap if the writing samples are wild, and this can make the problem of classification interesting. So when a new writing sample comes in that I want to classify, I might ask where in this 64-dimensional space this new point sits. And I will classify it as a J if it sits near the center of the cloud of J's. And there are two words here that need to be made precise: near and center. We need a notion of distance to talk about nearness. And to take a center, we need a notion of average, which means to sum the grids, whatever that means, and divide by the number of grids in my training data. And to divide by the number of grids is to multiply by a factor 1 over the number of grids. And as you can see, what didn't appear at first to be a mathematical object, a handwriting sample, now has a very handy description as something mathematical. And we need to do mathematical things with it, add them and multiply them, scale them by numbers. And the study of vectors will enable us to do these things. One way to think of mathematics is that it is the study of objects with certain kind of structure, and of functions that can preserve that structure. In linear algebra, the basic objects of study are vectors, and mathematicians like to think of them as having a certain kind of structure. Namely, you can perform certain vector operations like addition and scalar multiplication. The operations give a structure to the set of vectors by telling me how to do things with them. And the goal of this lecture is to understand vectors and their structure. Later on, we'll also study the functions that transform one space of vectors into another while preserving their structure. These will be called the linear transformations. Now, there are several different ways to define vectors, and that brings up an important point that will be true throughout this course. If there are several different ways to understand an object, we can use those different representations to our advantage. We can choose the way that makes the most sense for the task at hand. And passing back and forth between these representations can yield insight and understanding. Let's first talk about the geometric way to define a vector, which will be an object living in some space. We'll need to be careful about what space we're talking about. You and I live in a universe with 3 spatial dimensions that are evident to us, and a vector could live in this space. But we may also be interested in limiting ourselves to a 2-dimensional space, such as points on a plane, like on a sheet of paper. Or we might be interested in an n-dimensional space, which can arise in ways that don't represent physical space, but are still useful to think about geometrically, like a space of handwriting samples. When you fix the space you were talking about, a vector is a line segment in that space with a magnitude and a direction. If you've learned any physics, you might think of vectors as arrows in space that specify a magnitude and a direction. This is a geometric definition of a vector. We'll call one end the head and the other the tail. The arrow points in the direction moving from tail to head. So any two arrows with the same magnitude and direction are considered the same vector no matter where the arrow is placed. This notion of a vector as an arrow or a directed line segment shows why they are often used to represent things like motion, forces, or velocities in physics. Forces and velocities are things that have an intrinsic magnitude and direction. We can also define vectors algebraically. Another way that some think of vectors is as an ordered collection of numbers, like 3, 1, 4, or -1, 2.5, or 2, 3. This is an algebraic definition of a vector. The numbers are called components or coordinates, and for the most part, we will consider them to be real numbers, although they could come from any number system that is what mathematicians call a field. And we'll stick to real numbers for now. The set of all vectors with n components is called R to the n. Sometimes we just say Rn. The R with the double bar spine stands for the real numbers, and the superscripts remind us how many components the vector has. Remember, this is just a notation for a set of vectors. We're not doing anything like raising numbers to a power. We're just looking at a set of vectors and giving it a name. So R2 is the set of ordered pairs of real numbers, like 2, 3. The components could be written in a row vector, which means you arrange the numbers in a row, or as a column vector, in which numbers are arranged in a column. And whether we write vectors as rows or columns is just a matter of choice and will depend on the context. This view of a vector as an ordered collection of numbers is often used when working with data. For instance, you might look at a person and record 5 things about them: their age, their height, their weight, their income, their debt. That's a 5-dimensional vector. Or you might have a basket of 20 stocks and record how many shares you have of each stock. There's a natural correspondence between the algebraic definition of a vector as an ordered collection of n real numbers and the geometric definition of a vector as an arrow in n-dimensional space. To see this, one must first fix some coordinate directions. In the plane, we usually choose the x and the y-axes, drawn with the positive y-axis 90 degrees counterclockwise from the positive x-axis. Then a vector in R2 specified by an ordered pair of numbers like 2, 3 corresponds to an arrow in the plane that moves 2 units in the x direction and 3 units in the y direction. In 3-dimensional space, we usually choose the x, y, and z axes as coordinate directions. This is a good time to remark that there's a standard way to orient the x, y, z axes. Usually we demand that the positive directions along these axes obey what's called the right-hand rule. If you curl your fingers of your right hand in the direction from the positive x-axis to the positive y-axis, then your thumb will point in the direction of the positive z-axis. If we don't make this convention, some people will draw pictures that are the mere reverse of the other people's. You are probably used to drawing the xy plane on a sheet of paper with the positive x-axis pointing to the right and the positive y-axis pointing up. In this case, the positive z-axis will have to point up and out of the page. In R3, a triple of numbers like 7, 2, 3 represents an arrow in 3-dimensional space that moves 7 units in the x direction, 2 units in the y direction, and 3 units in the z direction. Similarly, every vector in Rn corresponds to an arrow that moves in certain coordinate directions by the amounts specified by the coordinates. This correspondence also suggests another way to view an ordered collection of numbers, not as an arrow in space, but as a point in space at the end of an arrow when you place the arrow's tail at a reference position called the origin. The numbers of the vector will then tell us how to get there in relation to the coordinate directions from the origin. Thus, the point that we call 7, 2, 3 is the point that is at the head of the vector 7, 2, 3 when you place the tail at the origin. In this view, every point in three-dimensional space can be represented by a triple of numbers, the same one that represents the vector from the origin. The origin itself is represented by the vector of all zeros, called the zero vector, since the arrow from the origin to itself involves no motion along any of the axes. In a similar way, you can choose to think of vectors in Rn as points or as arrows, and the choice we make depends on the context. For instance, if our vectors represent 5 bits of data about people in a population, we may choose to think of the vectors as points in a 5-dimensional space. If there are any correlations among the data, you might expect this cloud of points to have a special shape, and a data scientist might use the shape to investigate what kind of correlations there are. Okay, now I've just described for you two very concrete ways to define a vector, algebraic and geometric. The geometric definition is the picture you might have in your head. The algebraic definition is one that a computer might most easily work with. At the end of this lecture, we'll describe a third way to define a vector in a more abstract way. But before we do that, let's first see what we can do with vectors. Okay, now that we've discussed what vectors are, let's talk about the operations you can do with vectors. We've hinted at two of them, addition and scalar multiplication. And in describing each of these operations, we will present them geometrically, how you might visualize them, and algebraically, how you might compute them. The first basic operation on vectors is addition. To add two vectors, u and v, geometrically, you place the tail of v at the head of u, and look at the arrow formed by moving from the tail of u to the head of v. This is the vector u plus v. You can convince yourself that the order of u and v doesn't matter. If you add v and u, you get the same result. So vector addition is what's called commutative. The order of addition doesn't matter. Another way to view addition is to form the parallelogram with the sides u and v, taking their tails and placing them at the origin. Then an arrow from the origin along the diagonal is the sum of u and v. Algebraically, if you are given two vectors as ordered collections of numbers in Rn, the sum is just given by adding the numbers coordinate by coordinate. For instance, if the vector u is 1, 2, and the vector v is 3, -7, then our addition rule says 1, 2 plus 3, -7 is 4, -5, because we add the coordinates 1 plus 3 to get 4, and 2 minus 7 to get -5. You should check by drawing this out that the addition matches what is going on in the geometric picture. The new vector, 4, -5, says how far you have to walk in the x and y directions after walking according to the instructions given by the vectors u and v. Now another operation on vectors is scalar multiplication. A scalar is just a real number, but it gets its name when it behaves as a scaling factor for a vector by an operation called scalar multiplication. Geometrically, to multiply a vector v by 2, we just double its length while keeping its direction the same. So we've just scaled the vector by a factor of 2. To multiply v by 1/2, we just halve its length. We can also multiply by a negative number, which scales the magnitude but reverses the direction. So, for instance, minus v has the same length as v, but it points in the opposite direction. To multiply a vector by a scalar c, algebraically, we take every coordinate and multiply it by c. So 2 times 3, 1, 4 is 6, 2, 8. Soon, when we define the length of a vector in Rn, you will be able to see that this operation matches the geometric understanding that it scales the magnitude by 2 but does not change its direction. You might be wondering, since we mentioned addition, is there a subtraction of vectors? Why, yes, but it can be defined by addition and scalar multiplication. So if you want u minus v, you can just add u and minus v. And since u minus v plus v should be u, you can also see pictorially that if you place the tails of u and v together, then the arrow formed by moving from the head of v to the head of u is also u minus v. Scalar multiplication has what's called the distributive property over addition. C times u plus v equals cu plus cv. So it doesn't matter if you add and then scale by c, or if you scale by c first, then add. You can also see that scalar multiplication has what's called an associative property. If c and d are scalars and u is a vector, then c times du is the same as cd times u. Now that we have defined two operations on vectors, we can talk about what happens when we put them together. If you have vectors v1, v2 through vk, then a linear combination of v1 through vk is any vector of the form c1 v1 plus c2 v2 plus ... ck vk, where the c1 through the ck are scalars. So for example, 7 times the vector 1, 0, 0, plus 2 times the vector 0, 1, 0, plus 3 times the vector 0, 0, 1 is the vector 7, 2, 3. This shows that 7, 2, 3 is a linear combination of the vectors 1, 0, 0 and 0, 1, 0 and 0, 0, 1. By the way, the vectors 1, 0, 0, 0, 1, 0 and 0, 0, 1 have special names. They're called the standard basis vectors in R3, and they're often written E1, E2, E3. Physicists have different names for them. They call them I hat, J hat, and K hat. But that notation runs into problems if you have more dimensions. You might notice that linear combinations of the standard basis vectors will produce any vector in R3. This is one of the reasons we call it a basis, as we shall see later. But if you had just two vectors, you wouldn't be able to obtain any possible vector in R3. For instance, linear combinations of E1 and E2 only produce vectors whose third coordinate is 0. Often it's not so obvious whether a given vector is a linear combination of a set of vectors. For instance, what if I'm piloting a spaceship that sits at the origin and I have two thrusters that can propel me in two directions? Let's say 5, 1, 1 and 3, 0, -1. I want to know if I can reach the point 7, 2, 3. Do you see that this is really asking the question, does a linear combination of 5, 1, 1 and 3, 0, -1 exist that will produce 7, 2, 3? If we think about this abstractly for a moment, call these two vectors u and v. A linear combination of vectors u and v is any vector that can be obtained from doing addition and scalar multiplication on these two vectors. So it must be of the form scalar times u plus another scalar times v. For instance, -2u plus 3v is a linear combination of u and v. So is 1/2 u plus 3/2 v. The 0 vector is also a trivial linear combination of u and v, namely the scalar 0 times u plus 0 times v. Now, if you look at the set of all possible linear combinations of u and v, you can see that it'll form a plane as long as u and v do not point in the same direction. You may also be able to see that by fixing either the coefficient of u or v and letting the other coefficient vary, you will trace out natural coordinate lines along this plane. And in the figure, you can see where the 1/2 u plus 3/2 v is located. This plane cannot fill out all of three-dimensional space. Some points are clearly not linear combinations of u and v. We have a special name for the set of all linear combinations of a collection of vectors. We call that set the span of the vectors. So the span of u and v here will be a plane. And in the degenerate case where u and v point in the same direction, the span of u and v will just be a line. Now note that the problem of determining whether a linear combination will produce a given vector is the same as solving a system of linear equations for the coefficients of that linear combination. In our earlier example, if the coefficient of 5, 1, 1 is x and 3, 0, minus 1 is y, then we want to determine if there exists x and y such that x times 5, 1, 1 plus y times 3, 0, minus 1 is the vector 7, 2, 3. Looking at the components of this vector equation, x times 5, 1, 1 plus y times 3, 0, minus 1 equals 7, 2, 3, with x for the first unknown coefficient and y for the second unknown coefficient. This will be true if the following system of equations can be solved simultaneously. 5x plus 3y equals 7, x equals 2, and x minus y equals 3. We shall soon learn how to solve systems of equations using techniques of linear algebra. Now let's return to the character recognition problem. We've already seen that a letter sample on an 8x8 grid can be represented by an ordered collection of 64 real numbers. That's a vector in R64. We also have a natural notion of distance in R64. Just take the length of the vector difference between 2 points in R64. So the distance between v and w is just the magnitude of v minus w. And do we have a notion of average? Can we average all the letter j's to find the center of the cloud of letter j's? Of course we can. With 500 writing samples, the average letter j is just 1 over 500 times the sum of the 500 vectors, 1 for each sample letter j. Remember, these are vectors in R to the 64. We might end up with a grid that looks like this, representing the average letter j. We might have another such grid representing the average grid from 500 samples of the letter m. And a very simple classification algorithm would take a new sample and look at its distance from the average grid for each character and select the letter whose average grid is closest to the given sample. Now, this is a very crude way to recognize characters, and there's certainly better techniques. But if you're good at coding, you can try it out and see how effective this method is. Let's end with a discussion of the third way to define a vector. We've discussed vectors as arrows and as ordered collections of real numbers, which we can also think of as points in Rn. And we've seen that vectors can be scaled and added together in natural ways to form linear combinations. A third way to think of a vector is a more abstract way. For even though we mainly discuss vectors in Rn in this course, I want to encourage you to see vectors as more general objects that apply to a wide range of things that may not at first look like an arrow or as an ordered collection of real numbers. In mathematics, we often take our concrete examples and look at what properties made those objects interesting. Then we begin to define our objects by those properties. And when we do that, we realize that our methods for working with those objects were far more general and apply to other things. This is analogous to what happens when we call a cat or a dog a pet. After we play with cats and dogs a while, we begin to realize they have certain properties that make it a pet that are more general than catness or dogness. Namely, pets are living things you care for that make you happy. So this definition of a pet depends only on certain properties. And by this definition, many more things are also pets, like birds or hamsters. So if you look at how we use vectors, you see that we often do two basic things with vectors. We add them, and we scale them by making them bigger or smaller by some factor. We form linear combinations of those vectors. So a third way to define a vector is by what you might call an abstract definition, in which we define a vector by its properties. In this definition, a vector space is, loosely speaking, any collection of things that can be added and scaled together with some additional properties called axioms, which ensure that addition and scalar multiplication play nice by themselves and with each other. It doesn't matter so much right now that you remember these axioms that are displayed. They're just the properties we end up using when we prove anything about Rn. But the advantage of this definition is that we can now call other things vectors that weren't vectors before. For example, consider the collection of all continuous functions on the real line. If you're an engineer, such functions might arise as waveforms if you're doing signal processing. When continuous functions are added, you get another continuous function. And you can scale a continuous function by multiplying by a scalar, which changes its amplitude. This space of continuous functions satisfies all the axioms of a vector space, so it's another example of a vector space. Vector spaces arise very naturally in physics. For instance, in quantum mechanics, the state of a system is described by a quantum state. It doesn't matter so much that you know what that is. The important thing is that quantum states can be scaled and they can be added together. That's what's called superposition of states. So they can be regarded as vectors as well. The space of state vectors happens to be an infinite dimensional vector space with complex, not real, coefficients. As we shall see in coming lectures, the powerful ideas of linear algebra can help us understand abstract vector spaces as well.